14th edition of our functional analysis class. As I announced yesterday, today we are going to proceed with the Banach Spaces, and particularly we're going to look at the steps to follow when you are given a pair of a vector space or a linear space and a norm, and you are asked to show that this is a Banach space. What do you actually need to do? How do you have to proceed? We know already the definition. By definition, that a Banach space is a complete norm space. When I say norm space, it implies that it's a norm vector space. So it's quite simple, because by definition, the definition states that every Cauchy sequence converges. So it means that you take an arbitrary Cauchy sequence, arbitrary, meaning that it satisfies the definition for any epsilon. We can find a rank such that for any m and n greater than the rank, it will imply that the norm of the difference of x sub m minus x sub n is less than epsilon. If xn is our sequence, right? You can take fn, you can take xn, you can take tn. The notation is up to you, and it also depends on the circumstances. There are circumstances, for instance, if you are dealing with a linear operator, you will not take xn. Now you will take capital Tn, capital something, because for an operator operates on functions, for instance. You operate on functions, so your function will be f or x, but generally for function you will take f, g, h, things like that. And then if you take a sequence of operator, you take capital T, sub n, things like that. So that's what I was saying. You can take xn, you can take fn if it's a sequence of function. You can take capital Tn. So it depends. It depends on the circumstances or the environment or the type of space you are dealing with. Okay, so that is the assumption. So you write that definition, and from that definition, you proceed downwards until you reach R. As I mentioned yesterday, from the definition of your norm, or the distance from which you will extract the norm, from that definition, you will be able to go down to R in a certain manner. You have to go down to R from that space, make sure you reach R, using that same definition of Cauchy sequence. Once you reach into R, you use the fact that R is complete, meaning that that Cauchy sequence now in R will converge. Now, with the statement that it converges, you'll be able to write that it's converging towards a limit. That is in R, and then from R you go up again, because you went down, you go back up, right? Because when an angel comes down from heaven to earth, he has to go back, because he is sent for a particular mission. Once he reaches the mission, he has to go back, to say, okay, I delivered a mission, or this is what I brought, something like that. That's just an analogy. It's not exactly what happened. But that's for you to understand. So the purpose of leaving that abstraction, which I call being in heaven, right? When I say heaven, it means that it's like spiritually something abstract, something there in the mind. So you leave that space, now you come down to earth, like in R, where you know things, where you can manipulate stuff. Now, once you are there, in R, you find that, okay, I have a limit in R. Now, from that limit, you have to construct back, until you get a limit in the original space that brought you down. So that is, if you understand that roughly, things will be easy. So without any further ado, I'll go straight to the example that we did in class. step by step, we are going to write everything, and you see the steps, how we are leaving the original space. We go down to R, and from R, we go back to the original space where we have our converging sequence that we were looking for. So once you reach there for an arbitrary sequence, you just conclude that it's complete. If you succeed to prove that, it converges not in R, because it will converge in R when you go down. Now from R, you have to show that you can use, because in R it will be component-wise. In general, it will be in a certain component-wise. Now you have to compose and to make sure that now you will convert in the original space. So that is the idea behind. And we are going to go through an example where you will see exactly step by step how to proceed. I hope you will enjoy. Shalom. Okay, I'm sharing the slide with you. This is the slide. So we are going to look at the third example here, because remember that I said first and second one from the note that I shared with you yesterday. Just go through, read, and try to do this. So we'll go straight to the third example, which is here. I is the closed interval AB, and our space capital X is CI, right? Because remember, generally when we define, we say it's X, a pair X in a norm, right? In general, you say X endowed with a certain norm. This is an arbitrary norm, but now here, our X in this case is the set of continuous function on the interval, the closed interval I, and our norm, this norm is now the infinity norm, and we know how to define the infinity norm. The supremum, right? Take the supremum on the given interval, which is our interval, the closed interval AB. That's our I. So that's exactly what we are going to do. Okay. So from here, what I would do, I will open a new window, because we are going to write. I don't want to keep writing this because that's messy. What I would do, I'll open a new window, and from that window, I'll be writing. Step by step, I will be writing. Okay, so this is where we are. So what we are doing now, we are proving that. So here is example 3. So we are proving that so we let I to be the closed interval AB. So this is a subset of R, right? And now we say that the pair CI, when you see C, or C0 is the same, C or C0, just to say it's continuous. CI with the infinity norm is a Banach space. Is a Banach space. Okay, Banach. So it means that it's a linear space, right? We mentioned it, and surely you should have done that in linear algebra to show that a set of continuous function on a closed interval, or even on R, is a linear space. Of course, there are many ways to prove it, but we take that as a result. It's a linear space, and this is a norm, the infinity norm. In one of the examples, this was proved there. So you take this, it's already a norm space. Now you want to prove that it is Banach, right? So we know already that it's a norm space. Now to show that it's Banach, because don't lose the focus here. When you are asked to show that something is Banach, you have first to mention that it's a norm space, right? Except you are asked to prove it's a norm space. But in general, but you'll be guided anyway. In general, when you say prove that it's a Banach space, if the norm, if the function, instead of calling norm, the function that is given is not obvious to be a norm, you have to prove that it's a norm first. And you indicate that it's a linear space, maybe using a theorem or whatever method. And then the next thing to prove that it's complete. That's all. Right. So that's why either the circumstances will be in such a way that you know already that it's a norm space. You use that information, you go straight to the fact that it is complete. So you have to pay attention with that. So what I will be doing each time, I will first state that it is a norm space, right? And then we go to the main important point, because the main important point here is the completeness of the space endowed with the norm. So I will first put here that CI is a norm space. Is a norm space. All right, so this information, I take it for granted. Why do I take it for granted? This was shown to be a norm in the notes. I can let me quickly check and tell you which page of the note. You can find that on the I'm surprised I don't see it. I have the impression that no, I don't really see it here. I'm really surprised. Oh no, but it's there. Example 5 on page 8. Okay, let me share this first. So you can see this one on page 8, example number 5. This is C, AB, and you have the infinity norm. You have the infinity and the P norm here. So they are all norms on the closing interval AB. Right. Now I'm asking you to do that, but still I have the impression I saw a slide. I thought that I gave you that slide. When this was proven, it was proved. Wait. Because I'm still a bit confused because when I look at this, I don't see the details. Whereas something is not right. Non-space. Okay, let me go back. No, that's not right. Okay. So in this that I did not do that. Or maybe it was in a test or the exam or what. Okay. Okay, but I promise that I will, whether in another video or during the tutorial, please remind me, tell me when we can have a tutorial, maybe on tomorrow's Wednesday, yeah? Okay, I suggest, because it will be difficult to find a day, I suggest that on Friday, we have a 2 hours tutorial on Friday afternoon, maybe from 4 to 6, 4, 5, 5, 6, 2 hours. Please find a way, a mean or whatsoever to be there. You can take, I don't know, a 2 hours leave. No, but because 4 is not far from 5, 5:15, the time that you are supposed to leave. Or you can come late, and those who will be coming late, you can see what we will have covered from another student, right? Because if you start from 5, it's already getting late, you see. I can't really afford. I'll be there the whole day and I will be there till late. No, if you have to pay a price, you have to pay a price. For knowledge, you pay a price. Because that's even a sacrifice. Because I can just sit as I'm doing here and discuss with you, but there are things that it's better to be there online because I mean face to face. There are things that online will not replace. So, okay, so I hope you understand. So we will do that. I had the impression that it was somewhere, but still, I can't recover realizing that it's not there, but I thought it was there. Anyway, but we found a solution. If I get something that we can share or I can write it down in an extra recording, maybe I can do that, but we'll see. Okay, so, but at least the information is there. The information is there, that it is a norm. So when you read something, try to do it yourself. And I said some statement that, like example, like here, when you say this is a Banach space, and I even gave you, I uploaded a note here that shows that this is a Banach space, this also. So please take time to read. You cannot expect to acquire knowledge if you don't sacrifice. You have to sacrifice your time, you have to sacrifice your money, you have even to buy books, textbook you have to buy. I'm not the one teaching you that you have to buy books. At this level, you have to know, even from first year, you are supposed to buy books. To build your own library where you'll be going to consult extra information, things like that. If you want to check something, you just go, you open your book, you read. You have to have your own library. Okay, so this being said, let me go back. So it is a norm space, right? We use that result. And now the next thing is to assume that we have a Cauchy sequence of element of that, for that norm. So the second step after that, we have to state that it's complete. So CI endowed with the infinity norm is complete. Is complete. So this is what we have to show this, right? And for that, we take an arbitrary Cauchy sequence because these are functions, right? This is a space of function. And we know that in general, when we talk about function, we take f of x. F is a function. F of x is the value taken by the function at x, right? In general, I want to stress on this. When you say f of x is not the function. F of x is the value of the function at x. The function is f. When you call the name of the function, you are identifying the function, right? But that is I would say an abuse, or by default. But it doesn't actually make sense, right? When we say f of x, a function, no, we say a function f. So I was saying that a function is generally denoted by f, g, h, things like that. So now, if you want to construct a sequence, or if you want to select a sequence, we take f sub n. We say, let f sub n a sequence of functions, of continuous function, or a sequence of function, or a Cauchy sequence. We say a Cauchy sequence, fn. And we write what it means. So let's do that. Let I can write like this, fn. I can write it like this, like that. Let this be a Cauchy sequence. So you see that this is a set. It's a set because it has elements, right? And the elements are the f, f1, f2, f3 up to infinity. So each element is in Ci. So if I take the set, it's a subset of Ci. So the notation is important here. You have to understand what it means. Right? Because elements of these are sequence, are function, are continuous function. So if I take an element here, it's a continuous function. So this is a set of continuous function. So that's why I put it this way. Or I can also write it this way, like this. I can write this way, or I can write that. Because in many textbooks, you see this, or you can also write it this way. And here, you can still put n here, but it's not needed, right? But you can still do that. All these notations are equivalent. So let this be a Cauchy sequence. Of element of C, but this already tells me that each element is in CI. I don't need to specify of element of CI. It's already there, but if I do that, it will be like redundant, but it doesn't hurt anybody. We can still say a Cauchy sequence of element of CI, but it's already there in that notation. So be a Cauchy sequence. So that is, what does that mean? That is, for any epsilon positive, I can write it here, I can start writing here. For any epsilon positive, right? I can find a rank that depends on epsilon. So that's why sometimes we write it, there exists n, which is n epsilon, meaning that that n depends on epsilon. If I change epsilon, I will have a new rank. Let's say, for instance, I take epsilon is equal to 1/10. The epsilon, the n that I will have there will depend on that epsilon. N can be maybe 100. Now, if I take epsilon equal to 1/5, it might be 200, that rank from which the conversion will start. So that is why when you see this notation, you must understand what it means. That for each epsilon, if I change epsilon, the rank from which it will also start converging will also change. So that rank is not fixed, but it will change relative to the value taken by epsilon. Okay. So there exists this such that for any m, n, right, of course, obviously element of, such that once both m and n are greater, so you can write it this way. You can write on this in the same row, or you can write it this way: m greater than n, like this, n greater than n. These two will imply that for this infinity norm, fm minus fn, obviously for the infinity norm, is less than epsilon. Right. So this is the definition of what it means to be a Cauchy sequence. But now what I would do, because I say for any, now I will fix my epsilon to be an arbitrary, because this is the definition. So meaning that this is true for any epsilon. Now what I would do, I would take an arbitrary epsilon that I would fix. And with that arbitrary epsilon, I would do everything that I want. But because that is true for an arbitrary epsilon, whatever I will be proving, since epsilon is arbitrary, it will be true for any epsilon. So what I would say here, fix epsilon positive. Right? We have the same definition. So this is still true, right? I know that for this epsilon, this exists, right? So I can repeat, or I can use this fact already. Right, same, depending on that, such that for any mn, m, n both greater than that, this is exactly the same thing here. This implies that this norm, infinity norm, is less than epsilon. Now, what is the purpose here? We want to show that this Cauchy sequence converges to what an element that has to be in CI. It converges towards an element that is in CI, because if that element is not in CI for that norm, of course, when you say convergence, it converges with respect to the norm. But if that element is not in CI, therefore it cannot be complete. Cannot be complete. We know that in R, for instance, if you take R with this norm, which is absolute value, if I take, for instance, the sequence xn equal to n, if I take the limit when n goes to infinity is infinity, you see infinity is not an element of R. If I'm in R, I have a sequence of element of R because xn equal to n, for any n is in R. Now, if I take the limit, it gives me infinity. You see, infinity is no longer in R. So that's why we say diverges. Of course, when you see diverges. The limit, right? The limit, that limit is not already in R. Because remember that in the definition of limit here, we have to write the term of the sequence minus the limit less than epsilon. Now, you see, even if I take this sequence of element in R, it's finite. It's a finite number. But now, when I take minus infinity, that difference already is infinity. It's negative infinity. Now, with the absolute value, it gives positive infinity. But positive infinity is not less than epsilon, which is an element of R. You see, that's what we see diverges, right? Anyway, there are many ways to see diverges, but it's not complete. You can see from there. So the limit has to be in the same space. So, and that's what we need to do. Right? That's what we need to do. Good. Okay. Now remember that here we are in this space, which is an infinite dimensional space, Ci. We are here with that norm. Now we have to go down to R. Now open your eyes and see how we will dive into R. We are diving down. We are going down into R. So that this epsilon is fixed. Right? Okay. Now for this same Mn greater than epsilon, I have this result, right? So this implication, so I have all these that precede. So for the same implication, I will write this. We got, what is this by definition? This is the supremum of what? We all know that if I write supremum, for instance, absolute value of xn, where n is in capital N, for instance, this supremum, if for the xn, of course, if it exists, we call it m, right? If it's a number, it is called m. It's there, it exists. It's called m. So now this m, because it's a supremum, this is greater than or equal to for any n. Because this is the supremum of, because this is a set. You have this set, x1, x2, x3. This is the set. This set, because it's a supremum. In fact, this is a supremum of this set. So if we take the supremum of this set, is the same, right? But since this is a supremum, each element inside there is less than the supremum because we take the highest value. Obviously, there's absolute. I just took its absolute value. If I take each one of them. So this is greater than each one. That's why we write this. So for any n, absolute value of Sn is greater than is less than or equal to the supremum. So that's what I'm going to write here. So this implies that, because the definition of this is what is the supremum so the norm, I will take it, I will write it for a single the supremum for this case, our interval is I. So for x in I, which is the closed interval AB, if you read the information about compact spaces, you will see that we need a closed interval, we took closed interval because a closed interval is compact. We saw that any closed and bounded interval in R is compact. And each Fn, or the F there, are continuous functions. And there's a result that states that every continuous function on a compact set is bounded and reaches or attains its maximum. So that is why this supremum exists, and it's attained by an element there, because it's a compact, that interval is compact. So I can find an element in that closed interval such that f of that element is the supremum. Or in other words, anyway, it's enough. But we are not going to use that information. But what I want to say is that that supremum exists, right? So this is okay, the supremum of f of x, like this, right? Where x is here in the closed interval. So now you see that this is the supremum of which set? This is what I can write this as the supremum of this set. It's the same, eh? When you write like this, this is actually what it means. You take the supremum of this. So this is, by definition, this is what it means. Eh? In order not to write all this, we condense. This is like a compact expression for this. Because supremum, is, as you saw in real analysis, is a supremum of a set, and this is the set. This is the set. You take the supremum of all these elements. So, but if I'm a supremum of element, I'm greater than each element in the set, right? So this supremum, because the supremum is a real number, it is greater than or equal to every element in the set. And an element of the set is this one, right? And this is true for every I, right? For any I, for any x in I. That's how you can write it. If you want to say for any x in I, you can also write it like this for any x in I. It's exactly the same thing. Okay. Okay, so this supremum, then I can say that this, which is the supremum, is greater than or equal to each element in the set. What are the elements in the set? If I replace f with this, it means that, so I write from here, it means that absolute value, it means that for any x in I, absolute value of fmx minus fn x, like this one is exactly similar to what I have here, is less than or equal to the supremum, which is this one. Oh, I don't need to put the sup, I'll just write this. Fm minus fn infinity, which is from here less than epsilon. So this is what this also implies, because if A, let's say B is less than epsilon and A is less than B, it implies that A is also less than epsilon, right? You just come here, write your less than epsilon here, you see that this A is also less than epsilon. Right. So I will use this fact. This is like my A and this is my B. Then I can write that this is less than epsilon. So I can move from here to this fact. And now if I write this fact, you see that this is already in R. That is what I mentioned, that you have to dive down into R. And this step will give us that possibility. So let me call this. I need this. I need to label this. Okay, so I will label this F1. Equation 1, yeah. I will give it a name. This is a label. I label that by equation 1 because I will come back to this and you will see why. Now, from this one, so this implies, it's the same, I just remove, I'll get rid now of this. So this implies that I can take for any at the end there, or it doesn't matter. I can take this for any xi after epsilon, or I can keep before epsilon. It doesn't matter, right? So this implies that for any x in I, the absolute value of f m x minus f n x is less than epsilon. That's true for any x in I. Now if I fix, because since it's true for any, if I fix this, if I fix x I still have for this same epsilon, we saw that already that there exists that n, right? So I have all these up to here, and it will imply that. Now, what does that mean? Okay, let me call this 2. Fixing x in I equation 2, this one. Fixing x in I equation 2 implies that this sequence fn x, because remember that if I have a function at a particular point, now I am in R, right? Because by definition, when you take an element of Ci like this implies that the function f is defined from I into R, right? Because these are real value functions, right? Value in R. So if I take an element here, f of that is in R, right? So this is fixed because x is fixed. This x is already fixed. Now, if I take n like this, like in this case for each, this is for each n, this is what I have. So for a fixed n, fn is in R. Now, if I vary my n like this, I take the set with all the n varying, I have a sequence of element of R. This is what I want you to know. If n is fixed, f sub n of x is in R. Now, if I vary, if I take n equal to 1, 2, 3, I have many such points in R. Then this is a sequence of element of R. Now, this 2 tells me that this is a Cauchy sequence of element of R, right? So it implies that this is the Cauchy sequence, of elements of R, of elements of R. And we know R is complete. So I hope you saw where we're going, we're heading to. I hope you saw where we're heading to. We're heading to here. This is where we're heading to. Never forget what I said. We dive into R that we know. Of element of R. So what does that mean? That for this x fixed, this, because R is complete, and you see we have the absolute value. You see that now here we have the absolute value. So we are of element of R with the absolute value, right? Okay. So since R is complete, when you say complete with that absolute value, since R is complete, of course, you can just say R is complete without mentioning this, but you understand what it means. It's complete. Okay. Now, a limit exists, but that limit depends on x, because remember that this is for x fixed. If I change this x, fn with n varying with x fixed, it's a different sequence. I fix x. This x is fixed. For instance, it's as if I'm having, for x fixed, let's say x, for instance, is 2. Fn of 2. If n is equal to 1, 2, 3, f1 of 2, f3 of 2, f of 2 of 2 of 2, you have a sequence of elements. Let me just, to make things more clear, maybe you might ask the question, why am I taking this time? I can rush, you have an impression to understand why you don't understand, and tomorrow you'll be struggling. I would rather take all the time, all the necessary time to explain step by step so that it will be sealed in your mind once and for all. For you to understand why we do this, because tomorrow a question might pop up and you have no answer. I'm taking all this time to explain. So when you write, you understand what you are doing. Okay, now for that x fixed, that's what I want you to understand. Let me just construct a simple function. Let's say, for instance, fn of x is equal to 1 by x plus x plus, or let's say even take x by n, like this. X by n. Then let me just take this. So simple. Now I fix n. So if I fix x, equal to 2, what do I have? I would say Fn of 2 is just 2 by n. You agree with me that when n would change, you have a sequence of elements in R. So you already know that this is a sequence. This we can call it xn. This is xn, right? But because it's a sequence of function, it means that the x is also present. You can see here. It's not just a sequence, but it's a sequence of function. That is for n fixed, you have a function. All right? If you fix x, I mean n now. If you fix n, if n is fixed, say for instance, n equal to 3, right? So what is f3x? f3x is, and you recognize that this is a function in the variable x, right? So for each value of n, you have a function. If I fix n, I have a function. If n is equal to 5, I have f5x is equal to x by 5. This is a function. If I change, I have a function of x. So this is what we call sequence of function. As for varying x and a fixed n, you have a function. Now for fixed x and varying n, you have a sequence. So sequence of functions. So you have to play on both. Play on the function, play on the sequence, depending on what you want to do. So this is important. It's not a waste of time. So all these steps, explanation, remember I said I will be going step by step. So that all the questions will be answered in the process. Or maybe even if you never thought about this, at least this will come to enlighten you more. Okay, so I was saying, that this, when I fix x, I have a sequence. I have a sequence of real numbers. Sequence of element of R. So that's what I say here. Fixing x, as we did here, once you you assign a value to that x, it's a fixed value. You don't see x in your formula, but you see now n that is varying. That's exactly what we have here. So it is something of like this, where you don't see x anymore. You have been assigned a value, you only see the n. Now, if you take the n varying, you have a sequence of element of R, and that's exactly what we have here. And now that sequence of element of R will converge because R is and why would it converge? Because we have a sequence here. You can see here. For a fixed x, we have a Cauchy sequence of element of R. So that's why we have to fix. If I don't fix, I don't have a sequence of element of R. I have to fix. I have to fix to have a sequence in one of the variables. If x is fixed, it will be in a variable of n. That's a sequence. We are not talking about a function now. We are talking about sequence because x, the variable x that makes that notation of function is fixed. The value is assigned. Now, varying the n parameter, it is a sequence in the sense that you know a sequence. Okay, so the explanation now, I can erase this. I hope things are now clear. Now you will agree with me that the limit, of course, here the limit will be the same, depending on x, the limit will be the same. Because if I take the limit here, it will give you 0. This is a special case. But imagine that. Imagine, for instance, that instead of this, if I write this, let me write something else. If I take this, for instance, if I take, instead of that, if I construct this function, fnx equal to x into exponential negative n, negative plus 1. For instance, I'm just taking this example for you to illustrate something. I want you to see something with this. Now, if I do the same thing, I fix x equal to 2. You see that fn of 2 will be 2 by this. This is a sequence of element of R, right? Sequence, you see n, the variable here is a sequence. Now, if I take the limit now, when n varies, you see that this will converge to 2. Now, if I take n equal to, let's say epsilon, because 2 you will see, fn epsilon, which is epsilon, this will converge to epsilon. So now you see that this limit will change for each x. So it depends on x. So the limit depends on x. That's what I want you to see. Now, if I just say fixed, but I don't assign a value, I just say x is fixed. Now, if I take the limit here, so you see that this will converge. Fnx will converge to x. If I fix this, I take the limit, it will converge to x. You see that it depends on x. I can add, I can write x squared plus whatsoever, but it will convert to that thing, whatever I will write here, it will convert to that. So you see that the limit will depend on x. Of course, this was a special case where, regardless of I will give the same limit, right? But actually, in general, it depends on x. This is what I want you to see. If I fix x, I take the limit, I have a value. If I change, I have a different value. And this is how you can see it. So it depends, that limit depends on x. And this is important for the continuation. Right? So because the limit from the last example, that limit depends on x. Now that limit, I will call it f sub x, or L sub x, or L of x. So something that depends on x, right? So since R is complete, and this is a Cauchy sequence of element of R, this will converge towards an element of R, but of course it will depend on x, right? So this Cauchy sequence of element of R will converges to an element of R. That element depend, or the element depending on x. So we'll call it Lx or fx or f of x. So it's a function. I can call it g of x. I can give it any name, but to link it to the f, this f, I will call it f of x. So this is the limit of that. So it is called, that limit is called f of x. So that is the limit. So for x fixed, now this x is fixed. Now what if I vary x? Now if I vary x, I have a whole function, right? Now, so now I can define. We can define now for each x here, f of x exists as the limit of this. So now we can define this function. This at this stage, this is a number that defined, a number that depends on x. Now, if I vary x in I for each x, that's the definition of a function. To each element, I associate something. Now, for each x, I will associate the corresponding f of x. So that's a function. I have just defined a function. So we define the function f from I to R, so that for each x here, we associate f of x, the limit of this. So this function is a function. So now this function is continuous. This function is continuous, right? It is a continuous. You can prove it, or you can use a result from real analysis that state that a sequence of function that converges uniformly, the uniform limit of continuous function is continuous. So that's the result that I will use here for now, but you can still prove it. Even from here, you can prove it. You can prove it from here. Continuity, you can really prove it even from here. You can prove the continuity from here. From this, from 2. You just take the limit. You just take the limit here. Just take the limit. You take the limit. And ensure that there's uniform continuity. Right. Okay, now I will be having a class now. I'm having a class in 4 minutes. So what I will do, I think I will stop the recording and I will come back. I will proceed with the recording in the next, after an hour. Oh, we have already spent an hour. Oh, the explanation really took time. So I will come back from here. So what we will do, let me quickly explain what we will be doing next in the coming minutes, in the coming 1 hour. So what I will do now, I will remember that I labeled this by 1 and 2. So what I will do at this stage, I can even show you the uniform continuity from here, or the uniform convergence if you want. I can still prove you the uniform convergence. So I can mix everything and I can do everything here, continuity. I can use 1 or 2 to prove everything that I want. But what we are going to do now, we are going to prove that this sequence of function will convert to f in Ci with the infinity norm. So how are we going to do that? So what we are going to do in this 2, what I would do in 2, I will fix one of the subscript. Maybe I will fix n, and I will take n varying. M will vary. I will take the limit when m goes to infinity in 2. So if I take the limit in 2 when m goes to infinity, I will replace this by f of x. So we have this, and it will be less than or equal to epsilon, which doesn't make it, in fact, doesn't change anything. That will be the first result. And then from this, because we know that this will converge, I can do the exact same thing here. I will also take the limit. I can take the same limit here to show that it will converges. sorry, it will converge for the infinity norm, right? Or from that result, because it will be true for any x, I just apply the supremum here with less than or equal. If I apply the supremum, then I will move, I'll be going upward. I will already be in CI, right? So that's what we'll be doing. So I have a class in 1 minute. So sorry for the inconvenience. I will stop the recording now, and I will proceed in the coming hour. Thank you for your kind attention. God bless you and see you very soon.